One of the most generally noticeable physicists, Michio Kaku, has talked about his assessment concerning this issue. Kaku, known for his astounding contributions to the fields of physical science, has recently acknowledged that the James Webb Space Telescope has discovered 6 enormous cosmic systems that researchers once thought couldn't exist. These discoveries have the potential to open up new perspectives in our understanding of the universe. It is therefore both fascinating and worth keeping an eye on these developments. Kaku is an exceptional figure in the scientific field, a physicist of American and Japanese heritage. He is viewed as an expert in both traditional experimental physics and quantum mechanics. Unlike some more conservative and skeptical scientists, Kaku does not belong to that group and has been open to the astounding later findings of the James Webb Space Telescope (JWST) mission. We are fortunate that this distinguished researcher has decided to end his silence and share openly what can no longer be denied. The excitement and nearly universal tone of the renowned physicist is evident in his remarks on the discoveries made by the James Webb Space Telescope. He suggests that these findings have been the feature that has energized his interest. Let's explore the implications of Michio Kaku's discovery of these 6 gigantic cosmic systems. Kaku is a scientist who has always been able to contemplate new theories throughout his life. He understands that Einstein's theories of relativity and Newton's laws are inadequate to capture the full complexity of the universe. Kaku realizes that the discoveries of the new telescope could potentially improve the scientific field, even though many of his peers have not been able to embrace this view. This has caused concern and restlessness among both defenders and critics of quantum mechanics. Nevertheless, this honest insight evokes laughter from Kaku. The JWST has uncovered the discovery of 6 massive universes dating back to the earliest stages of the universe. Each of these cosmic systems contains more stars than our own, despite forming only a short time after the Big Bang. The team of astronomers who made the discovery has named these remarkable systems universe breakers, as their existence would change our entire understanding of the universe. Something here no longer fits with the theory of the Big Bang. The Big Bang theory tells us that the universe was a chaotic place immediately after the initial event. The first solid objects took several 100 million years to form, and it took countless additional years for these objects to reach a sufficient density to produce light. The development of complex structures like galaxies was expected to happen much later. Some of the newly discovered systems surpassed the size of the Milky Way, and their enormous brightness suggests that they were likely forming many new stars every year, while our own galaxy forms stars only sporadically. It remains unclear exactly when the first universe is formed. Scientists have not been able to determine this until recently. The one thing that is clear is that initially there may have been only single stars or groups of stars that eventually came together to form progressively larger structures, ultimately leading to the development of dwarf galaxies, which underwent mergers and gradually evolved, as indicated by previous theories. According to these theories, very advanced and massive systems could not have existed at that time, which raises the question of whether the universe is significantly older than previously believed or whether complex, large-scale structures existed much earlier than expected. This situation is challenging for conservative science, which still struggles with this model. Moreover, some areas of physics have strongly rejected this discovery, pointing to potential errors in the age calculations. Kaku, aware of this, had this to say: there are many instances of old and misleading theories that stubbornly persist due to the prominence of certain researchers. Many of these theories were eventually disproven when basic analysis revealed their falsehoods. Thus, the key work in any science, particularly in physics, rests with the experimentalists who maintain the validity of research through empirical truth. In fact, on Earth, we have virtually no knowledge of the true origins of the universe. The Big Bang theory was established in 1927 based on observations of the universe's expansion. This data led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was hard for people and scientists to imagine a universe with a beginning and an end. The possibility of a universe that had always existed and was infinite in time was beyond human imagination. Even today, scientists still face challenges in understanding it. However, it is critical to reconsider these possibilities. These new insights don't fit at all with what scientists have relied on for decades in the Big Bang theory, yet science has repeatedly shown that reassessment and openness to groundbreaking ideas are key parts of the scientific process, just as much as the confirmation of specific theories and observations. When Einstein was a child, it was believed that the stars and planets were fixed in the universe and that these specific arrangements occupied a defined space. However, we now understand that everything in the universe is in motion. Planets orbit stars, stars move within their galaxies at different speeds, and entire galaxies move rapidly through space, the ultimate fate of which we still cannot predict. Today, scientists are challenged to accept uncomfortable truths, and it is understood that theories are not merely speculations or fundamental truths until they are rigorously tested or confirmed by exact observations. The concept of the Big Bang emerged from the confirmation that galaxies are moving away from each other, and this distance is proportional to their separation from Earth. This observation, known as Hubble's law, suggested that the universe has been expanding for a long time. Additional evidence like cosmic microwave background radiation and the red shift of light from distant galaxies and other astronomical structures seems to support this theory. However, it is important to remember that people who once believed the Earth was flat and that the Sun revolved around us also had similar kinds of evidence for their doubts until events or technological advancements provided a clearer and more accurate picture. Currently, we are witnessing a similar situation. Scientists expected the JWST to confirm assumptions about the Big Bang, but instead, they have discovered 6 systems that appear to be too large for their age. This reminds us that science is always advancing, and researchers must remain open to new discoveries and reassess existing theories in light of available evidence. Scientists use redshift as a tool to determine specific measurements in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to each other. To understand this, imagine watching a car coming toward you. As it moves closer, you hear the engine getting louder. However, once the car passes you or moves away, the sound changes. This is because the sound changes as the car moves. The same is true for light. Conversely, when the light source moves away, the light shifts toward redder shades. This phenomenon is known as redshift. Physicists have converted redshift values into speeds and distances for measuring quantities in the study of the universe. However, it is crucial to note that small errors in these calculations could have huge implications. The measurement methods used in the past are now under review, and the results that scientists will arrive at regarding the latest discoveries related to our universe are intriguing. It is important to consider whether these results are truly based on redshift errors or whether some researchers are simply denying the facts. This is a question that requires serious evaluation and careful review of the data and methods used in the research. As scientific inquiry progresses, discoveries made by instruments like the James Webb Space Telescope often challenge our assumptions about the universe. The recent discovery of 6 massive galaxies dating back to the early days of the universe is one such example. These galaxies, which defy typical hypotheses of galaxy formation, raise important questions about the timeline and processes associated with the development of large-scale structures. The James Webb Space Telescope, a successor to the Hubble Space Telescope, is equipped with cutting-edge technologies that allow it to peer further into space with remarkable clarity. Its ability to detect light from the farthest reaches of the universe provides astronomers with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive galaxies challenges existing models that predicted such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond astronomy and into the realm of fundamental physics, compelling scientists to rethink established theories about the early universe. These discoveries also highlight the importance of staying open to revolutionary ideas and modifying our understanding in response to experimental evidence. Kaku has emphasized the critical role of scientific proof in shaping our comprehension of the universe, pointing out that theories must constantly evolve to accommodate new information. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, there are proponents who argue that the discovery of early massive galaxies suggests a longer timeline for cosmic evolution than previously thought. This perspective challenges the traditional view that galaxies evolve gradually over billions of years through mergers and the steady development of smaller objects. On the other hand, skeptics warn against hastily discarding established models based on limited observational data. They advocate for a cautious approach, suggesting that anomalies in data interpretation or measurement errors could explain the unexpected findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a critical role in these significant investigations. As galaxies move away from Earth, the light they emit shifts toward longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy's light spectrum, astronomers can infer its distance from Earth and its velocity relative to our own galaxy. This information is essential for developing models of cosmic evolution and understanding the distribution of galaxies in the universe. Furthermore, the James Webb Space Telescope's ability to detect faint infrared signals allows it to observe galaxies that would otherwise be obscured by dust and gas in the early universe. This capability is crucial for studying the formation of stars and galaxies during the universe's infancy, a period known as the cosmic dawn. By examining the light emitted by these distant galaxies, astronomers can trace the chemical composition of the early universe and gain insights into the processes that led to the formation of the first stars and galaxies. Beyond its astronomical implications, the discovery of these early massive galaxies raises philosophical questions about the nature of scientific progress and human understanding over time. Scientific principles have shifted based on new discoveries and observations. What once seemed impossible or speculative eventually becomes accepted as new evidence emerges. This iterative process of theory, observation, and revision is central to the advancement of knowledge in all scientific disciplines. The idea of a paradigm shift, as articulated by philosopher Thomas Kuhn, describes the profound change that occurs when anomalies in existing theories prompt a major reassessment of scientific principles. The discovery of early massive galaxies pushes astronomers to reconsider their understanding of cosmic evolution and the processes that led to the galaxies we observe today. It underscores the importance of remaining open to revolutionary ideas and revising theories in response to empirical evidence. Astronomers and astrophysicists are also grappling with the implications of these discoveries for our understanding of dark matter and dark energy. These elusive components, which together account for a substantial portion of the universe's mass and energy content, play a vital role in shaping the large-scale structure of the universe.